No, set theory. Set theory is an important branch of mathematics. Perhaps it is the fundamental part of mathematics. The theory was developed by the German mathematician George Cantor. George Cantor. George Cantor, who lived in 1845, 1948. 1948. A famous German mathematician. And now, by a set, we usually think of the literary meaning. In the literary sense, a set is a collection. A collection of objects, collection of things, collection of persons, or collection of numbers, any collection. Usually we mean this by a set. But in mathematics, it is a collection, not only a collection, but a well-defined collection. A collection of well-defined objects is set in mathematics. So what is the meaning of this well-defined collection? Well-defined collection means the collection is defined well, very well. Means, or we may explain that term using certain examples. So consider the collection of the first 10 natural numbers. Collection of first 10 natural numbers. So the numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the first 10 natural numbers. Now, another collection, consider the vowels in English alphabet. Vowels in English alphabet. So the collection consists of A, E, I, O, U. Then another collection of eminent 5 mathematicians of India. 5 eminent mathematicians, names of 5 eminent mathematicians. 5 eminent mathematicians of our country, India. So consider these 3 collections. The first collection, the collection of first 10 natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this collection is the first 10 natural numbers for me. For you also the first 10 natural numbers is this. And for some others, or for any person, the collection is this, the same collection. Second collection, the vowels consist of this A, E, I, O, U for me, for you, and for any other person. The collection is this. The collection is the same. But consider the third collection, 5 eminent mathematicians. For me, I may write 5 names. 5 names. And you also will be writing 5 names. That 5 names need not be exactly the same as that I have written. Can be another set, another collection, another collection. For some others, the collection may be different, again different. That means this third collection is not defined well. If we have a collection, then an object can be said to be definitely or without any doubt that the object belongs to the collection or not. That should be able. We can say, or we should be able to say whether an object belongs to that collection or not. or not? The third collection is not such a collection. If we have an alphabet, then we can say, suppose we have the alphabet Z, then we can say that Z does not belong to this collection. If we have the number, say 200 or minus 15, we can say that number does not belong to this collection. But if we are given the name of a mathematician, we cannot definitely say whether that name included in the collection which I or you have written. It may or may not come in the collection of 5 eminent mathematicians. That collection depends upon the nature or the behavior or the decision of the person who write the names. That is the case. The collection may vary from person to person. So such a collection is not well defined. That is the meaning. And now, this set in mathematics is a collection which is well defined. A collection of objects. A collection of well-defined objects is called a set in mathematics. We can have a few more examples. Consider the set of all integers. We know the set of all integers, the collection of all integers. It is a set because the integers are well defined. For me, for you, and for others, the collection is same. The collection is same. So it is a set. But the names of 10 rivers in Kerala. 10 rivers in Kerala. It is not well defined because from persons to person, the collection may be different. Not different. So the collection of 10 rivers in Kerala, not well defined. But the names of all rivers of Kerala, the collection consisting of the names of all rivers of Kerala, it's well defined. Cannot be changed from person to person. So such a collection is called a set in mathematics. Okay. And usually the sets are symbolically denoted by these capital letters A, B, C, or this X, Y, Z, etc. And an object in this set usually denoted by small a, small b, small c, or small x, small y, small z. So this collection 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 can be denoted by a capital A. But we have to specify what does it mean. The capital letter A means capital A is the set of first 10 natural numbers. Then we can write the set as capital A for convenience. And then if you want to represent the set, there are mainly two methods. Representing means writing all the objects in the collection. The objects in the collection are also known as the elements of the collection, elements of the set, or members of the set, etc. and so on. Objects, elements, members, we are using interchangeably for the objects in the collection. And now, if we have a set, well-defined collection of objects, then we can represent this set by two methods. the first method is the tabular form or roster form. The tabular form or roster form. And the second is the set builder form. Tabular form or the set builder. In the tabular form, what we do is we list all the objects separated by comma and put those objects within the curly braces. This curly braces like this, bracket like this. List all the objects. Write all the objects separated by comma and put or cover that by this braces or put that objects within this bracket. So in the case of the set of natural numbers, first 10 natural numbers, if the set is denoted by, symbolically denoted by capital A, then we write the set as in the tabular form or roster form, this A is equal to, then the bracket, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and close. So this is the representation in the tabular form or roster form. Tabular form or roster form. And now we see that this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are members of this A or objects of the set A or elements of the set A. And if A is an element of this capital A, the set A, symbolically it is denoted by this A, this symbol capital. This is the Greek letter epsilon. This symbol says this element, this A, is an object in this collection capital A. If A is not a member, then it is denoted by the symbol A, this epsilon, then a cross. This means A naught belongs to this A element of A, or A belongs to A, or a member of A. Here it is not. A not element of A not belongs to this A. Here A belongs to A. And therefore, in this situation, this 2 element of this capital A, 10 element of this capital A, and so on. So this is the representation in the tabular form, representation of the set A in the tabular form or in the roster. And now again, there is another form which is the set builder form. Then set builder form is a form with which we build the set. We build the set. We are building the set. So that means we represent all the elements in the collection by a single variable, usually denoted by x. That means, suppose we represent this like the set of first 10 natural numbers using this method. That is, this A is equal to, then put that also in the bracket. The member in the collection is represented by a representative, usually this x. Then we define this x by specifying its characteristic. How this x belongs to the set. How this x can be an element in the set. Here, we usually draw a slash, which means such that. So this means collection of all x such that what type of collection we specify. X is a natural number. A natural number. Completed. Then 1 less than or equal to x less than or equal to 10. It's okay. X is a natural number. 1 less than or equal to x less than or equal to 10. All such x's. This means not a single element. This is a representative. This means collection of all x. Satisfying this explanation. X is a natural number. 1 less than or equal to x, less than or equal to 10. Then what are the possible values of this x? 1. X can be 2. X can be 3. X can be 4, 5, 6, 7, 8, 9, 10. So this means collection of all such x's. So it's okay. The collection is clear. The numbers 1, 2, 3, etc. 10. That is the collection. So this is in the set builder form. We are building the set. This is a representative of the set. This representative says here what I am. This x says I am a natural number and I range from 1 to 10. That is the method of building a set, and this is the set builder form. This also can be used to represent a vector. We want to put this within this curly braces. Opening brace, closing brace. So this is the method of representing the set in the set builder form. So we can have certain examples. So suppose we want to represent the set of natural numbers, collection of all natural numbers in these two forms. Then in the first form, the set consists of, so list all the members of the collection. So 1, 2, 3, 4, 5. Then listing all the members means we want to write all the elements. But practically it is impossible because the set of all natural numbers consists of infinitely many elements. In that case, we usually use a technique, that is, write some numbers and then use this dot, etc. This means this dot says the remaining portions after this 5 is those numbers which match with this. So 1, 2, 3, 4, 5, then the next is 6, then 7, 8, 9, etc. And here this dot continuing. So that means goes to infinity. The list continues to infinity. So this is enough. This is enough. Listing all the elements can be taken in this sense also. In the case of infinitely many elements, we can write this. But if we use this dots should specifically say the elements in those portions. This is written in a specific order, and that order continues. That order continues. If the numbers listed in the first phase are not in a specific order, then there is no use of using such dots. Consider some numbers, say 2, -3, 0, 1 by 2, 8, 10, 25, -13 by 2. Then If you dot after this certain dots, this dot cannot say the next number because this was no specific order or rule. We cannot write the next number or the next number after this next. So here it is impossible, but here it is possible. In this situation, this set can be indicated by using these dots also. Okay, remember that. So this is the representation of set in the form. And now the set of all natural numbers in the tabular form or roster form is this. And in the set builder form, the set is represented by set of all x, collection of all x, such that, for that word such that, use either a slash or a colon. This is also enough. This means a collection of all x, such that, then specify the characteristic of x, how this x belongs to the collection. X is a natural number. Close the bracket. This is enough. No restriction for this x in the case of this collection of all natural numbers, as in the case of this first 10 natural numbers. There is a restriction for x. X maximum value of this x is 10, ranges from 1 to 10. Here no restriction, such a restriction. So we say x is a natural number. So collection of all x, where x is a natural number means this collection is set of all natural numbers, the collection of all natural numbers. So this is the representation in the set builder form, and this is the representation in the roster or tabular form. So that is the case. We can have more examples when we discuss the exercise. Okay. And now we have defined a collection of well-defined objects as set, and also the representation of a set. How we can represent? We can represent in two ways. The first method is the tabular method or roster method, and the second is set builder method. Okay. And now we have different types of sets. The first is null set or empty set. Null set or empty set. So by empty set we mean which is a set but it does not contain any element or object. It is a set but it does not contain any element. For example, consider the students in your school. The collection of all students in your school studying in both +1 and +2 class. A student is studying in both the classes +1 and +2. That is a collection. We define such a collection. It is well-defined collection because consider the definition of a set. That collection is a collection that should be well-defined. If you have a student, you can say without any doubt that whether the student belongs to the collection or not. You are able to say. That is enough to define a set. And now consider the collection of all students studying in both +1 and +2. No such student. A student cannot study in +1 and +2 at the same time. Therefore, it is an empty set. No element, but by definition, it is a set. And the empty set is usually denoted by the symbol, this symbol, phi, or an empty set denoted by this bracket, curly braces, but within this bracket, no element, no object. But remember that this is not an empty set. This is a set in which this phi is a member. Phi is a symbol in this case. It's a representing symbol. It's a member. This is not an empty set, but this is empty or this is empty. So usually we use either this or this to represent an empty set. That is a definition. And again, a set consisting of only one element is called a singleton set. Singleton set. It contains only one element. Only one element. You can have a number of examples. But it should contain only one. Only one number. Okay? For example, consider your school. The collection of principals of your school. There is one and only one principal. There can be vice principal or assistant principal, but we define the collection as the collection of principals in your school. Not vice principal. Principal in your school. Your school will have only one principal. So the set consists of only one element. One element. So such a set is called a singleton set. And now we define equal sets. And this is important. This is important. Now, before defining these equal sets, we have to understand the definition of the set very clearly. Consider the set consisting of the first 5 natural numbers. Suppose it is denoted by A. A equal to 1, 2, 3, 4, 5. First 5 natural numbers. And then another set B, which is equal to 1, 2, 3, 4, 5, 6, 7. Okay. Then another set C, which is equal to 5, 4, 3, 2, 1. Then next one, D, 1, 2, 3, 4, 5, 4, 5, 1. Consider these sets. This set A consists of 1, 2, 3, 4, 5. B 1, 2, 3, 4, 5, 6, 7. This is a set different from this here. This consists of 5 elements and this consists of 7 elements. The first is 7 natural numbers, first 5 natural. And this C consists of 4, 3, 2, 1. 4, 5, 4, 3, 2, 1. This also consists of the first 5 natural numbers, but the numbers are written in some other order. In A, 1, 2, 3, 4, 5. In C, 5, 4, 3, 2, 1. This also consists of the first 5 natural numbers. First 5 natural numbers. Okay. And now consider this D. 1, 2, 3, 4, 5. Then again 4, 5, 1. 4, 5 and 1 repeated again in this collection. But even then, we see that this consists of the first 5 natural numbers. First 5 natural numbers. Then we check this A, C, and D. We know the first 5 natural numbers are 1, 2, 3, 4, 5. We check whether all these elements, these 5 natural numbers, belongs to these sets or not. 1, it's a member. 2, it's a member. 3 member. 4 member. 5 member. Okay, this collection is collection of 5 natural numbers. 1 is there, 2 is there, 3, 4, 5 there. Therefore, this is also the collection of first 5 natural numbers. This 1 is there, 2 is there, 3 is there, 4 is there, 5 is there. Then one more time 4, one more time 5, one more time 1. But anyhow, we see that this collection consists of the first 5 natural numbers. In the definition of the set, nowhere it is said that an element cannot be repeated. Element is not repeated. Therefore, this collection is also the collection of first 5 natural numbers. First 5 natural numbers. So this is the collection of first 5 natural numbers. This is the collection of first 5 natural numbers. This is also the collection of first 5 natural numbers. That is, in a collection, an element can be repeated and repeated in any number of times. That does not affect the very definition of the set. Okay, remember that. And now we define the equality of 2 sets. 2 sets are said to be equal if they contain the same elements. If they contain the same elements. In the definition of equality, there is no specification of the position of elements, the order of writing the elements, or the order in which the elements are written in the set, or whether there is repetition or not. Set. Nothing. Definition is, if the 2 sets consist of the same elements, in this A we have 1, here also we have 1, here also we have 1, same elements. 2, here also 2, 3, 4, 5. Okay, then here again 4 repeated. 4 repeated. But even though this 4 is repeated, we see that it is an element in the set. 4 is an element in the set. Also repeated 5. Again, element in the set, Therefore, we see that these 2 are equal. These 2 are equal. These 2 are equal. If the 2 sets consist of same elements, the 2 sets are equal. That is the definition. Okay? And again, finite sets and infinite sets. Finite set and infinite set. Finite and infinite. So from the name itself, we can say, what does it mean? Finite set means if a set consists of finitely many elements, finite number of elements, it is a finite set. The set of first 10 natural numbers is finite set. Set of all natural numbers is infinite set. Infinite set is a set which is not finite, or it is a set consisting of infinitely many elements. If it consists of infinitely many elements, means it is not finite. It cannot contain, it contains not finite number of elements, but infinite number of elements. That is the definition. So if the set consists of finitely many elements, it is finite set. Otherwise, that is, if the set consists of infinitely many elements, it is an infinite set. And now consider this empty set phi. There is no element in the set, but even then it is defined to be finite. So the definition of this finite set can be like this. The set empty set or a set consisting of finitely many elements, finite number of elements is a finite set. Otherwise, it is an infinite set. That is the definition. So finite set and infinite set. Okay? And now there comes subsets and supersets. Subsets and supersets. Subsets and supersets. And now consider a set A and another set B. Another set B. If every element of A belongs to the set B, A is said to be a subset of B. A is said to be a subset of B. Every element of A is an element of B. Every element of A belongs to B. Then it is a subset. A is a subset of B. It is a definition. In that case, B is said to be the superset or superset of A. If A is subset of B, then B is superset of A. That is the definition. For example, suppose this A is equal to 1, 2, 3, 4, 5, and B is equal to 1, 2, 3, etc. 10. First 5 natural numbers, first 10 natural numbers. Then take this first number, 1, element of this B, 2 belongs to this, 3 belongs to this, 4 belongs to this, 5 belongs to this. So this A is a subset of B. And in this case, this B is a superset of B. Superset of B. And if A is a subset of B, then this fact is denoted by the symbol, this A, then A symbol. This symbol indicates A is a subset of B, and we read A subset of B. A subset of B. If A is not a subset of B, then this symbol is used. The first symbol for subset, then a slash, cross it. So A not subset of B. This can again be written in the reverse order. This B, A subset of B, or we can read from left to right. B superset of A. B superset of A. So this B not superset of A. That means A not subset of B. So in this way, we can write the subsets and the superset in symbolic form. And now consider this B is equal to this 5, 4, 3, 2, 1. Then 1 element of this B, 2 element of this, 3 element of this, 4 element of this, 5 element of this. That is, this A and B satisfies the very definition of subset of a set. That is, here this A subset of B. We do not verify whether the B contains more elements or not. The definition is this. If every element of A, element of B, then A subset of B. Here that definition is satisfied. So here A subset of B, that means this A equal to B that we know. That means A subset of A, every set is a subset of itself. Every set is a subset of itself. That is the meaning. Okay. If every subset of every set can be a subset of itself, then that fact is symbolically denoted by this. That is A. This means A can be equal to B also. In that situation, in such a situation, if A equal to B, then we write this symbol. If B contains at least one element more than that of this A, in this situation, this A is said to be a proper subset of B. So in this case, A and B, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, etc. 10. In this case, this A is a proper subset of B. Proper subset of B. B is a proper superset of A. Okay? So that is the situation. If we know the element or the set B such that it contains more element than that of this A, then only we specifically say this A is a proper subset of B. We do not know. We only know A is a subset of B. Every element of A belongs to this B. We do not know whether this B contains more elements or not. In that situation, what we can do is we simply say A is a subset of B. B is a subset of B. And if we know clearly that B contains more element, distinct element other than that of this A, we can say A is a proper subset. Otherwise, we simply say A is a subset. So that is the definition of subset. A set can be a subset of itself. Subsets of itself. And again, consider this. In this case, A subset of, in this case, A and B. 1, 2, 3, 4, 5. B consists of also this 5, 4, 3, 2, 1. That is 1, 2, 3, 4, 5. Order is not actually a factor in the case of this set, but just written. So in this case, we see that A subset of B and also B subset of A. A subset of B and B subset of A. This is the indication that A equal to B. This is possible only if A equal to B. A subset of B and B subset of A, though both together is possible only if A equal to B. And therefore, this is used to prove two sets are equal, A equal to B. In problems, there are many situations in which we want to prove two sets are equal, A equal to B. Then in this case, what we do is, we first prove A subset of B. That is, show that every element of A is an element of B. Then prove in the reverse. Every element of B is an element of A. Then B subset of A. If A subset of B and B subset of A both hold, then A equal to B. That is the method. That is the way in which we prove two sets are equal. Okay. So thus we have seen the definition of a set, example, some few example, and the representation. Representation of sets, and also different types of sets. Null set, singleton set, then finite and infinite sets, subsets, supersets, representation, equal sets, equality of sets. Okay. And the next remaining part can be seen in the next episode. Okay. We are writing up here, and we will see next in the next video. Okay. Thank you.